This lesson is about arc length, sector of a circle, surface area, volume, and capacity. So let's start with arc length and sector. So we're dealing with a circle. Usually the name of the circle is based on the center of the circle. So this would be, for example, circle A, or sometimes we'll use this symbol circle A, so that way that's the name of that circle, but that's neither here nor there, just in case you encounter that. So the part of the circle on the outside, like that, from B to C is called arc BC, and usually the symbol, sort of a curvy thing at the top for arc BC. What we're interested in is how big of an arc, how long is that arc? Now, in order to do that, I'm going to think of the entire circumference of the circle and then figure out what fraction of that whole circumference that arc is. So I have what's called the central angle. I've labeled it theta. That's the angle that the arc makes at the center, and that allows me to figure out what fraction of the entire circle the arc length would be. So the fraction of the circle is going to be, I take the angle, whatever it might be, and I divide it by 360, because 360 would have been the entire circle. So how many ever degrees theta is, I divide it by 360, that'll tell me the fraction of the circle. And then I multiply now by the 2 pi r, because 2 pi r, of course, if you remember, that's just that's the circumference of a circle. C equals 2 pi r. So I want only a fraction of that circumference. So the 2 pi r is the circumference, and I multiply by the fraction, which is theta, out of the entire 360, and that gives me the arc length, in this case, of this arc from B to C. That's the formula for arc length. Now, a sector of a circle is basically a pizza slice kind of a thing created by drawing two radius or radii from the center out. So you're slicing this like a pizza with two cuts. And so this region is called the sector, and we have an area for that. Now, once again, to get the area of the sector, I need to know what fraction of the whole circle I'm dealing with, and then I need to compare that to the area of the entire circle. Now, the fraction of the circle is going to be theta out of 360, because 360 would have been the whole circle. So whatever theta measure, whatever angle I get, I divide by 360. That tells me the fraction of the circle. And then I multiply that by the area of the entire circle, which is pi r squared. So this there is the area of a circle. So I take the fraction of the circle, theta over 360, and then multiply by the area of the whole circle to get the area of the sector. So here we have an example. Find the perimeter and area of the shaded region. Well, the shaded region is this one. There's an arc length here, there's another arc length here, and then there's these two sides over here. So let's talk about the perimeter. I would have to add this number plus this number plus this number plus this number to get the perimeter of the shaded region. This red stuff doesn't affect the shaded region. However, to figure out the arc length, for example, of this one, I need to think of it as a fraction of a circle. That big circle would have been all the way around like that, and the radius of that big circle would have been 7, 5 plus 2. And then, of course, the fraction of the circle is 110 divided by 360. So if I label, let's say I labeled this one, I don't know, A, and then I'm going to label this one B, and then, of course, I've got my 2 over here, and I'm going to have my 2 over here for the total perimeter. So to get A, I need to do 110 over 360, and then times 2 pi r, so 2 pi. And then for this outer arc length, the radius of the circle there would be 7. So it's 2 pi times 7. Now B, on the other hand, well, now again, it's the fraction out of 360, still 110 out of 360, that fraction times the 2 pi r, in this case times 2 pi. And now the radius for that smaller arc length is just the 5, so 2 pi times 5. So I plug both of these into my calculator, and I keep all the decimals because it's the middle of the problem. So the A value that I get is 13.43903 524. And the B value that I get is 9.599310886. So now I can calculate the perimeter. The perim is going to equal what's going to be the 13.43903524 plus the 9.59931080886 plus the 2 plus the other 2. So it's that distance plus this distance plus this distance. And I plug that into my calculator. And now I'm going to round to the generic 3 sig figs that IB expects. And I get approximately 27.0 meters. Now I want to do the area of that region. Well, the area of that region, it's a big sector minus a small sector. The big sector would be the sector with the radius of 7, and the small sector would be the sector with a radius of 5. That would leave me with just the shaded region. So the area is going to be, well, I need to take the fraction of the whole circle, 110 divided by 360 times the pi r squared, but it's the pi r squared for the big circle first, or big sector, so pi 7 squared. And then subtract from that the area of the smaller sector, so 110 over 360, same fraction, times the pi 5 squared, because that was the radius of the smaller circle, or the smaller sector. And again, I can plug all of this into my calculator. And again, I round to 3 sig figs, and I get approximately 23.0 meters squared. Now, be very careful to make sure you use the pi button on the calculator, not 3.14. We are way more sophisticated than that. 3.14 is just good enough for maybe middle school. But once you get to high school, pi has to be the button on the calculator, not 3.14. All right, so let's talk a little about surface area and volume. There's basically a lot of formulas you need to know. Many of them are on the formula sheet, the IB formula sheet. They're in 2 places, unfortunately. One of that places is in the prior learning, which is toward the front of the formula sheet or formula booklet. They talk about the area of the curved surface of a cylinder, which is A equals 2 pi RH. Then they talk about the volume of a cuboid, which you would just call a box, length times width times height, the volume of a cylinder, pi r squared h, the volume of a prism, volume equals A times h. A is the area, what they call a cross section, but I would call it the area of the base times the height. So those formulas are all in the prior learning section. Then they also have formulas in section SL 3.1, which is a few pages later, so you got to look them up over there. The area of the curved surface of a cone is A equals pi RL, and L is called the slant height, and I'll show you what that looks like in a picture in a few minutes. Then the surface area of the sphere is area equals 4 pi r squared, so that's another formula, that's for a sphere. Then they have the volume of a right pyramid, V equals 1/3 A times H. A is now the area of the base, and which is why I like to call this area also area of the base. No reason to use a different name for it. And then the volume of a right cone is 1/3 pi r squared H. And the volume of a sphere is 4/3 pi r cubed. So these formulas are in section SL 3.1 on the formula sheet, and these are in the prior learning sections on the formula sheet. So I want to point out to you that a lot of times those formulas are not actually going to be useful. So for example, you were not given the surface area of a pyramid, but you can still figure it out. The surface area of the pyramid just means add up the areas of all of the surfaces of a pyramid. This one is a square base. It said so right there. And then it has these 4 triangles on the sides, right? There's one on this side, there's one in the front, there's one on the back, and there's one on that back. You were told here that the height is 10.8 centimeters. The height is from the very top of the pyramid, also known as the apex of the pyramid, right down to the middle of the base. So that H there is the green. H equals 10.8 centimeters. And then the base length, well, the base is the square at the bottom in this case. It doesn't have to be a square, but this one was a square, is 13.2. So that's 13.2. And of course, that and that and that are also 13.2, I suppose I should say, centimeters. Now I put this blue thing in here on purpose. This is the perpendicular to that one side of the pyramid. That is called the slant height. Slant height. So it's not the actual height of the pyramid, it's the height on the slant side, or in the slant sort of face in this case. And the variable we use for slant height usually is L, whereas the variable you use for regular height is H. So that is necessary because the regular height is not the height of anything that's in terms of surfaces, the height of the entire pyramid, but it's not the height of any of the surfaces. The slant height, on the other hand, is the height of this triangle, and of course the four triangles are all identical, so once you get one of them, you multiply by 4 to get the total area. Now, in order to figure out that slant height, we have to do a little bit extra work, and what I mean by that is we need to extend this line all the way to there and redraw this triangle like this. Where this side over here was the height, which was 10.8. And this side here was the slant height, which is L. And then this side down here is this length. Well, that should be right in the middle of the base of that little square. So it should be exactly, that distance should be exactly half of that 13.2. So it's going to be 6.6 centimeters. That's 13.2 divided by 2. And now that I have that, and I know of course there's a right angle right there, I can use Pythagorean theorem to work out what the slant height is going to be. So here we have L squared equals 10.8 squared plus 6.6 squared. And I can plug all that in my calculator. Of course, ultimately I need L equals the square root of that, 10.8 squared plus 6.6 squared. And now technically I should be doing plus or minus square root, but obviously a slant height or length cannot be negative, so I can ignore that part. So I'm going to plug this into my calculator and keep all the decimals. So I get 12.65701,387. That's what the calculator reports to me. And so now I'm ready to calculate the surface area of this pyramid, because there's the base, the bottom surface, and there's the four identical triangles. So the surface area is going to equal, well, the area of the base at the bottom is just the area of a square with a length of 13.2, so it's 13.2 squared. Plus, then I have to do 4 triangles, so 4 times, and then the area of a triangle is 1/2 base times height, so 1/2, and then the base of that triangle is going to be the 13.2. And then the height of the triangle is actually the slant height, not the original height, so this 12.65 number. Keep all the decimals at this point, 12.65701,387. And then I plug all that into my calculator. And now I round to 3 sig figs, and it's going to be approximately 508 centimeters squared because it's an area. All right, some more surface area problems, saying rounded to 1 decimal place, so we'll get to that when we get to that. So this looks like a cylinder to me. The radius of the cylinder is 6, the height of the cylinder is 14. So, and it says no top. So there's a circle at the bottom, and then there's the curved surface, which is also called the lateral surface, and that's it. So the total surface area, I have to add the circle area, which is pi r squared, so pi 6 squared, plus the lateral or curved surface area, which the formula sheet tells me is 2 pi RH, so 2 pi times 6 times 14, and I plug all that into my calculator and then round to 1 decimal place, and I get approximately 640.9 to 1 decimal place, and of course it's centimeters squared. Now this next one is a sphere. It's the whole sphere, so I don't have to adjust the formula. So the formula for surface area is 4 pi r squared. So it's 4 pi, and the radius here is 5, and then squared. And again, I plug that into my calculator. And I get approximately 314.2 centimeters squared. Now this last one is a cone, and if you remember the formula for the curved surface or the lateral surface of the cone is pi r L. L is the slant height, which would be this height. This is the regular height, h. So I need to find the slant height. Let's label it L right there. So you can actually see the right triangle sitting right there. L is the hypotenuse, so I can do L squared equals 8 squared plus 15 squared, and of course I can do L equals the square root of that. And you should get 17 when you're done. And so now I have the information I need, the surface area of this cone. Well, first of all, there's the circle at the top, so pi r squared, so pi 8 squared, plus the lateral or curved surface, which is pi r L, so pi 8, and then 17, and I ignored the 15 entirely, and again I plug that into my calculator, and I get approximately 628.3. And that would be, again, centimeters squared. All right, so now we're going to do volume. So first of all, this one is a cylinder, so the volume of a cylinder is pi r squared h. Well, I don't know the radius, but I do know the diameter, so the radius is just going to be half of that, so 18. So that's going to be 18 millimeters. So the volume is going to be pi r squared h, so pi 18 squared 45, because 45 is the height of that cylinder. And I just plug that into my calculator. And with 3 sig figs, I get approximately 45,800 millimeters cubed. All right, for this one, this is a prism. It's a triangular prism because the base triangle here and the base triangle here are identical. And then it's got this height here, which is, in this case, slanted, not slanted, back and front, but it's still the height. The base here and the base here are the repeated shape, and then that becomes the height. So I need to know the area of the base and then multiply by the height. Well, the base is a triangle. These two markings say it's actually an isosceles triangle. So let me redraw just that triangle that looks like this. That's 12, that's 10, that's marked as the same as that. So that's also 10. Well, I need the 1/2 base times height, so I need to know the base and the height of this isosceles triangle. The best thing to do here would be cut it right down the middle symmetrically and make this then half a 6 and try to figure out the height. Let's call it h. And because I cut it down symmetrically and made a right triangle, I can use Pythagorean theorem. So I can say 6 squared plus h squared is going to equal 10 squared. And when you solve that and you get h squared equals 10 squared minus 6 squared, or h equals the square root of 10 squared minus 6 squared, you should get 8 as the height. So now the volume of this thing then is going to be the area of the triangle first, 1/2 base times height, so 1/2, and then the base was 12, and the height for the triangle was 8, and then times the height of the prism, which is 30. So there's two different heights here you have to keep track of. One was the height that was inside the triangle, and the other is the height for the prism. And so I plug that into my calculator, and I don't have to round this one. It's just 1,440 centimeters cubed. Now this one is a pyramid, so the volume of a pyramid is 1/3 area of base times height. Now luckily it gave me the actual height, not the slant height. So I've got the height I want, and the base is a rectangle with all these right angles in it. So the volume here is going to be 1/3, and I first do the area of the rectangle, which is 5.1 times 2.3, and then I multiply that one times the height of the pyramid, which is 6.8. 8, and I plug that into my calculator. And again, to 3 sig figs, I get approximately 26.6 centimeters cubed. So now let's briefly talk about capacity versus volume. Capacity measures how much a container can hold. It basically is the interior volume. The only difference, though, is that we use different units. We say 1 liter for capacity, whereas for volume we would call that 1,000 cubic centimeters. So you need to know this conversion. 1 liter equals 1,000 cubic centimeters. The symbol for liter is capital L, and of course centimeters cubed for cubic centimeters. So let's do an example. All right, we're asked to find the capacity of a 2.6 meter by 3.1 meter by 1.45 meter tank. This sounds like a rectangular prism to me, or what the textbook or IB calls a cuboid, or what you might call a box. So let's find its volume first. So the volume is going to be 2.6 times 3.1 times 1.45, and I plug that into my calculator, and I get 11.687, and I'm going to keep all the decimal places here. It's the middle of the problem. And the units, of course, are meters times meters times meters, so meters cubed. Now I want to find the capacity, not the volume, so I need to convert this meters cubed into liters. So let's think about the conversions that we know so far. Well, first of all, we know that 1 meter equals 100 centimeters. We also know that 1 liter equals 1,000 centimeters cubed. So this should give me what I need to work out the conversion. I can get from meters into centimeters, and then I can take centimeters cubed into liters. The problem, though, is this is meters cubed, not meters. So this conversion by itself is not going to help. So the first thing I'm going to do is I'm going to cube both sides so that I end up with cube, or meters cubed. So 1 cubed is just 1, and then meters cubed. And then 100 is cubed is going to be 1,000,000. Or if you want to write 10 to the 6th, that's okay. And then centimeters cubed. Now, I want to convert this 11.687 meters cubed by canceling out meters cubed and then eventually canceling out centimeters cubed. So let me recopy the 11.687 meters cubed. 11.687 meters cubed. And I'm going to divide it by 1 for a second. And now what I'm going to do is I'm going to multiply it by 1 a bunch of times, because that doesn't change anything, but I'm going to be clever about what I use for 1. So let's see. I've got this 1 meter cubed equals 1,000,000 centimeter cubed. Right now I have meter cubed in the numerator, and I'd like to get rid of it. So I'm going to put meter cubed in the denominator. So I'm going to divide both sides of this equation here by 1 meter cubed. So I get 1 equals 1,000,000 centimeter cubed over 1 meter cubed. So I can multiply this 11.687 meter cubed over 1 times that 1,000,000 centimeters cubed over 1 meter cubed, because basically I multiplied by 1 and didn't change anything. Now that gets me to cancel the meters cubed, so let's do that. This meter cubed will cancel with this meter cubed. But now I've got centimeters cubed. I still don't have liters. However, I do have this conversion over here to get liters out of centimeters cubed. Centimeters cubed right now are in the numerator. I want to put them in the denominator to cancel out, so I got to rearrange this to make it equal to 1 by dividing both sides by 1,000 centimeters cubed. So 1 liter over 1,000 centimeters cubed is going to equal 1. So again, I'm going to multiply by this version of 1 now. So I multiply by 1 liter over 1,000 centimeters cubed. And again, I notice that here the centimeters cubed will cancel with the centimeters cubed. And all I would be left with now is liters, which is what I want. So now I take the 11.687, multiply by 1,000,000, divide by 1,000, and I end up with 11,687, but of course I wanted 3 sig figs, so I'm going to say 11,700 liters because those are the units that I was looking for. So that is the capacity of this tank, or whatever it might be. So again, I found its volume first, and then I needed to convert from, in this case, meters cubed into liters, and I had to use my conversion from meters to centimeters, and of course cube that, because the meters centimeters on its own doesn't get me what I want. Cube that, and then I created versions of one for my different conversions that will allow me to cancel out the units that I have and leave me with units that I would prefer. So I can take it from meters cubed into centimeters cubed, and then centimeters cubed into liters by multiplying by this version of one, and then by this version of one, the meters cubed and the centimeters cubed eventually disappear, and I get my liters. And that's the end of the lesson.